Today, we'll be taking a look at this thing called exponential growth, and we're actually going to take a look at the exponential model. So now, when we talk about exponential growth, we're talking about things where, basically, there's some form of percentage growth over a certain amount of time. Now, some common examples are population growth, price increases, and compound interest in bank accounts. The basic equation that we're working on is the same thing that we were looking at yesterday. So remember, we were looking at this thing, y equals ab to the exponent x. Now, you need to recognize the a value is the initial value, and the b value is what we call the rate of growth. All right. Now, later on, we're going to call that b value a growth factor. Now, we discussed that in the previous lesson, and today we're just focusing on this thing called we'll call it a growth rate for now. Now, so if we know that something is growing, we know that b is bigger than 1. So that would mean b is bigger than the number 1, which means it's growth. So our graph is going to kind of look something like this. Okay, where this is our initial value and things like that, and then this part here represents our increasing values. Now, another thing that I want you to remember, just try to remember, we're always going to try to refer to this as the start. The a value is the start, and the b value could also be looked at as the ratio that we multiply by to get to the next number every time. So now let's take a look at this problem that we have here. So the price of new homes increases at about 3% each year. The value of a $175,000 new home can be modeled by P equals 175,000 bracket 1.03 to the x. So this green part here represents the initial amount. Now, the initial amount is always the a value that we started with, or otherwise known as the start value. Now, the second part, this part that's inside the bracket, the thing that's raised to the exponent, is greater than 1. So this is b. So, and notice it's greater than 1. That means this is growth. And in order to find how we got that, you got to think of it this way. B is equal to the number 1 plus, think of it, 3 divided by 100. Remember, our original percentage was a growth of 3% per year, which gives us, when we punch it in our calculator, 1.03. Isn't that interesting? Now, let's move on to the graphing of our problem. So one of the things it says is I want you to sketch an example of this graph. This is our basic equation. We said that the initial portion of our graph, or where our graph started, was at 175,000 on the price axis of our equation. So because it's p equals that, the p goes on the up and down version of the axis, and then along the y on the x-axis we have time. So when we graph this, we literally just sort of make it swoop up. So this is basically p is equal to 175,000 times 1.03 raised to the x. Now, the first question that it asks us is, what is the cost of the home from 5 years from now? Now, it's actually asking us, knowing that x is the number of years in the future, so then it's saying, well, x is equal to 5. That is what we have to do, and we're going to sub that into our equation. Now, that's what we get. Punch that in, and you're going to get this as your following answer. Unless I say otherwise, give me the answers to nearest dollars, because you as a homeowner don't really care about the cents. What we do care about is the dollars that I make out of my home sale. Let's move on to the next problem. Now, this next problem says, what will the new home cost 10 years from now? Let's do the calculations just like before. Just like before, x is 10. We substitute. Now, upon substitution, you're going to get this. So you end up with 235,185. So now just remember, all we're trying to do today is to make sure we understand how we model these situations, and then also interpret certain things from those equations. So one of the things that I want you to recognize for this next problem says we have some bacteria. It says that the bacteria doubles every 4 hours, okay, that have passed by. Now, the population can always be modeled by this problem here. So if I put an arrow to the 5 here, the 5 represents the start. Now, the start of this colony literally starts with 5 bacteria based on our equation, and that matches, that kind of gives you an idea of how many bacteria started. Now, the growth factor, that's the B value. In this case, it's the 2. And in this case, our growth factor is B is equal to 2 in this case, which means that it doubles every X block of 4 hours. So isn't that what we said here? It doubles. So this equation does work for what we're looking for. Now, this X value is based on the multiples of 4-hour blocks that pass by. So let's see where I got that from. Let's read the last bit. Now you notice every time you get these problems, you have to read into the next bit of the problem set where it says where X is the number of 4-hour periods that have passed by. So that's where we get the number of 4-hour periods. So if 4 hours passed, X would be 1. If 8 hours passed, X would be 2, and so on and so forth. Now let's go and do the calculations. Now, what was the initial population of the bacteria? Like we said before, it was 5. Now, if you're not sure if that's correct, then this is what you do. Just go and check. If X was equal to 0, you'd substitute directly in and you'd get y equals 5, 2 to the exponent 0. Y is equal to 5 times 1. So that means y is equal to 5, which is what we expected.